Yes.
Yeah, yeah. I have prepared. I have looked at the code, so I have prepared some slides on my understanding. So, what exactly is Microwatt? Microwatt is an open source software processor. So, it is developed by Power ISA. It was originally started by IBM. Uh, it implements the Power ISA architecture. So, it was, as we all know, it was written in VHDL. It can run on bare metal, but it also supports like Linux OS and some other light OS like Zephyr and OpenSPI. It supports some basic peripherals like UART and SPI. So the intent was to make a small processor, to make a processor, full functional processor with a small footprint, uh, specifically for FPGA prototyping and also for educational purposes. So when we look at the ISA or the instruction set architecture, it has 32 GPRs or general purpose registers. So it has 64-bit architecture. It supports both 32 and 64-bit instructions as well as defined in Power ISA. It supports integer instructions, and there is also support for FPU or floating point instructions, but the support is pretty limited. So it operates in supervisor mode, which allows the operating system for the full resource access. And then it supports both big and little endian support. It supports both of little endian and big endian generation. And there is an also option for memory management unit. It supports Linux booting with MMU. So it can run without the FPU and MMU, but we can choose to have it in our design. So it's a basic five pipeline architecture. It is similar to RISC-V. So most of the architecture is pretty much the same. So it has 5 stages, like fetch, decode, execute, memory, and write back. So there are no out of order execution or speculative execution. It's a basic in order execution. So no branch prediction as well as simple branch prediction handling, no simple branch handling. And it has typically has two caches, instruction cache and data cache. We can choose to implement multiple levels of caches, but not necessarily in basic Microwatt. So it just has some instruction cache and data cache. So we can have options of MMU and TLB in some versions if we choose to have it. TLB translates to you know translation cassette buffer if I'm not wrong, and MMU both helps in virtual addressing. So as discussed earlier, it was supposed to be for FPGA, synthesized on FPGA. So since the goal was for educational purposes, uh, the Microwatt core is designed to be basic, but has an option to extend it. So whenever we, basically write a design or design something, the final end goal is to generally to synthesize it and put it in a physical chip, manufacture. So when we do that, Microwatt is not a standalone thing. It needs some peripherals to control and all that. So in order to communicate with other components and peripherals, it needs some interface, right? So the IBM chose Wishbone as its interface. So it has a benefit. So if I want to extend my implementation, and let's say if I want to have an MMU or any some other external course, I can simply take the IP course and integrate it with it. Since most of the IP cores support Wishbone protocol, it makes it simple to integrate it with this. So it also supports general GPIO operations. So this is I have done a block diagram of my basic high level understanding. So we can see multiple components here. So we see the big brain, which is the core, and there is also system controller and Wishbone DRAM wrapper, which is necessarily a BRAM or block RAM. And we see these peripherals, two UART blocks and GPIO. And then these are the XICS, ICP, and ICS, which act as a pair. Then necessarily IBM's interrupt controller system. so which helps communicating with the peripherals. And there is the flash memory. It usually stores things like BIOS, Linux imagine. Sometimes, if our SoC doesn't have a DRAM specifically, uh, it also stores the main program so that when the boot code loads up, so the main program from the SPI would be loaded onto the BRAM, and the main program starts executing from the BRAM. And we also have these two blocks which are helpful for debugging. So DMI is a protocol used for debugging, or we can say read or writing the debug registers to access them. So that is a protocol. These blocks helps in, let's say, uh, I want to test this when I implemented it in FPGA or some physical board. I can use protocols like JTAG to physically test them. So the protocol JTAG would be the input to this DMI DTM, and it converts it to DMI. And since the core communicates, core and all the other peripherals communicates through only Wishbone fabric or Wishbone protocol, this block acts as a bridge and converts this DMI into Wishbone and then communicates to all of this. We can see the core implementation. So this is the basic pipeline. So we can see the fetch, which helps in fetching the address. Excuse me. Uh, Sorry about that. So fetch one, which helps in fetching the address from PC and feeds it to iCache. So iCache further uses some blocks like cache RAM and PLRUFN and predecoder. Predecoder is nothing but it decodes the instruction in advance for the cache RAM to use them. So cache RAM is simply a memory structure to store the data, all the instruction iCache. And PLRUFN is basically a PLRU function, which is pseudo least recently used protocol, which is used in caches for as a replacement for policy, and to maintain cache coherency. And we have uh, excuse me, and we have the decode blocks. We have two blocks for decoding, and we have register file where our operands are stored, and we have CR file or control register file, and some choose to name it as SPRs, which are special purpose registers. These usually hold the status and control data of the code. And then execute is where the real execution happens, and contains blocks like rotator, logical, multiply, divider, which simply executes the arithmetic functions or logical functions. And there is the FPU and MMU, which are optional, but we can include them. FPU helps in floating point operations, and then there is an MMU, which helps in virtual addressing and load store architecture, load store. So our Microwatt uses load store architecture, which essentially means that all of the executions are done on the registers, which are 32 register we are talking about earlier, GPR, general purpose registers. So since there are only limited number of registers, if we want to run many program, I mean a big program, they are not sufficient. So the load store architecture states that we can use an external memory, and we can use instructions like load and store to move from and to uh, registers from the memory, and then operate on the registers. And we also have data cache, which is similar to iCache. It simply stores the data, where iCache simply stores the instruction cache. And there is a write back, which write backs to register. That's the block. And there is a block called code debug. Uh, this helps in knowing the status and the internal registers of or of the core during debugging. So it also has configurable parameters like has FPU, has BTC, and EX1 bypass. These simply you can toggle them, or by changing them, you can choose to have an FPU or branch target cache and bypass logic in on your core. And also there are cache parameters which helps us in parameterizing the size, the block, the set of the cache, so that we can configure cache according to our needs. And there is a thing called ALT reset address. Uh, if we choose to have a DRAM initialization firmware, it usually helps in that. So when system powers up or an SOC powers up, it need to execute the program, but it is usually stored in DRAM if we have a DRAM. But until the DRAM is initialized, we can't access the DRAM. So, but to initialize the DRAM, it has some modules like load mode registers, so that we can configure the time parameters and more of the DRAMs as things like that. So we need to configure them, and to configure them, we need some program to run it. So it is simply called a boot program or boot code, which is pointed by this ALT reset address. So this address points to that boot code. So when the SOC powers up, it simply fetches the instruction pointed by this address and simply executes the boot code to initialize all other components like DRAM, and then prepares the SOC for main execution. So this is the fetch one. It simply has a program counter. Program counter simply stores the address of the next instruction or the next instruction to be executed. So it simply fetches and feeds it to the iCache, and it can also halt signals the pipeline to halt if necessary, say during branch decision or during debugging, things like that. Then it feeds to the iCache. iCache shows the instruction data, and when this address is given to that, it gives the data to decode block. And there are actually our instructions are encoded in machine code, and it has some bit fields to say what is the type of operation, what are the registers, and what are the address uh, that need to be done. These are all encoded in bits of fields. So the first decode stage identifies the simply identifies the address of the registers. So these addresses are fed to the address decoders of the GPRs, and then uh, the that specific data in the registers are fed. Fed to the execute as output. Uh, Decode one does that, and decode two. We have multiple types of instructions. Like, let's say simple add instructions might access two registers and write back to same register. So it operates on two registers and write back to the register. But if I want to add an immediate value, like let's say from R1 plus an immediate value called 15, so it has a bit fields. So one of the operator need to be a register, and one of the operand need to be a immediate value. So for that, we need some opcode to know what of the type of instruction we are executing, what is the type of instruction, what is its value, and also if we take a 32-bit instruction, so typically an immediate value is, the operands are 32 bits, but the immediate value only has 12 bits. We need to extend those 12 bits to 32 before can extend those and operate on that. So things like that. So for all these things, we need some control signals to operate. So decode 2 handles this decoding of control signals as well. And then the register file, it simply holds our operand values and sends the data to the execute block. CR file stores the condition code status and control information. Then execute code simply executes what uh, it was fed through the operands, and simply drives it to the load store block and or write back. It can also forward to fetch, uh, depending on the instructions and data dependencies. So then the load store architecture, this block usually accesses the memory for load store operations. It also interfaces with Dcache and MMU if MMU is present. Dcache simply holds the data, and then MMU is used for translation of address from virtual to physical address. It also signals the TLB, which is TLB misses and page faults as well. And there is a write back. It simply writes back to the register file and debug. This block constitutes to debug and is used for debug. It monitors the PC registers and also it can also trap fault signals during debugging. Let's say when there is a page fault or something, when the processor issues an error, I can simply stop at that point and see what is the status of the core and what are the address of specific registers and all of that. So we can look at the other components of a SOC. Is simply system controller, a block RAM is a debug transport module, which simply translates, it acts as a bridge between DMI and external interfaces like JTAG. Wishbone is a bridge which converts the DMI to Wishbone. And UART is a peripheral used for serial communication. You can connect it to any peripheral on an FPGA or any other peripheral. And then we can also use it to communicate with the serial console. Then there is a flash memory and there is an interrupt controller. Then the GPIO. GPIO simply states that if I connect a pin of the processor let's say an LED, I can choose to switch on that LED at specific interval times. So my processor generates some code to toggle these pins on and off at specific time intervals set by us. So it drives the LED. So things like that. GPS are used for general purpose communications. So core receives any interrupts from the peripherals and communicates via DMI. System controller typically has a configuration status register for the SOC, and then it also controls, consists informations like SOC version, reset control, clock frequency, clock configuration, everything such like that. Sorry. And then there is the block RAM, which is used for no main program running if there is no DRAM. So we can choose to have no BRAM if the BRAM size memory size is 0. Then there will be the main memory interface. It is generated. It generates acknowledge with on ones. And there is DTM, as said earlier. It converts JTAG signals to DMI, and the wishbone converts the DMI to wishbone, and UART communicates. And SPI typically stores things like BIOS, main program, and Linux image, things like that. So coming to the XICS, these two are two different models, but acts as a pair. ICS does mean that it's an interrupt controller source. It doesn't communicate with the core directly. It is a direct point of communication for peripherals. Peripherals typically communicate to ICS, and ICS sends to ICP, which is an interrupt control presenter. It presents the interrupts to the core, and so that core acts on it. So how this works is, since it is a memory mapped IO, peripherals are generally issued or assigned an address in the memory. So specific address is reserved for a specific peripheral. If I read or write to the address, I can control the peripheral. So there are usually two different types of mechanisms in microprocessor controllers, which is the polling and interrupts. These are the two main things. So polling is something that processor needs to see if any peripheral needs service continuously, and it needs to monitor it 24/7. So that is the mechanism. And interrupt mechanism, it states that processor does its own work, but whenever a peripheral needs a service, it signals the code through an interrupt. So then the processor simply stores the address of last instruction in a specific register and stops that program. And there it triggers a program called ISR, which is called interrupt service routine. This services the interrupt and starts after servicing the interrupt, it continues its main program. So when a peripheral needs generates an interrupt, it was sent to ICS, and ICS sends it to ICP, and ICP through wishbone communicates it to core, and core does the ISR, and then continues its program. Then that is how it works. And GPIO is a simple bidirectional GPIO to generate interruption or You can test the protocols on that, and you can control peripherals, things like that. So this is the code flow. Simply after power up, the clock will be active, and the reset will be asserted and propagated to all lower blocks. And then core fetches from VRAM, which is simply a boot port or boot program. So after it initializes all the peripherals and other components. Then they wait for access from core. And then if there is an interrupt, it was communicated to ICS, then ICP, and then core. And if we want to access, debug it, we can do it through DMI, and SOC is ready for full operation. So power up and reset, simply, powers up and resets all the Intel blocks, and clock and reset distribution distributes this reset signal to every other blocks. And the core initializes this instruction cache, data cache, GPS, and program counters, all of these things. Then the boot memory starts up and initializes everything. And then BRAM is instantiated and initialized from RAM init file if it is present. And then core access through BRAM through Wishbone, where main program executes. Wishbone fabric is used for communication. So there are usually two masters, a core and debug master as well, and every other component is simply a slave that responds to the master. And there are peripherals, which are UARTs and GPIO and SPI flash memory. As said earlier, this is the pair which acts as interrupt controller, and it services the interrupts. And then there is the debug infrastructure. If we want to debug it, we can use it. And there is the simulation exit option. There is a thing called sim. I believe it's a parameter. And if it's true and there is a special rights to DMI to address, it simply exits. And this is the recap. So it simply powers up, then the reset sequence, then the core initializes, and then core executes it. And it was sent to peripheral and simply executes it. So this is the basic understanding. So that's my presentation.